we said whatever y is here, I just want to get it probably just directly, probably a quick way. This by definition, just instead of x, you've got mn, so just put mn here. Okay, so that will give you G inverse mn G. Okay, now we're trying to show that this is Fm times Fn. Now I can rewrite this, watch, G inverse M, G inverse, bit of a trick, but it works, right? All I've done is I've just put an E in here. I put, between M and N, I just put in the unit E, which is of this form. And I did that deliberately because this G inverse M of G, G inverse M of G is just M, right? So I can rewrite that. I can rewrite that as F of M, right? And similar argument here. So that's F of M. All right. So you've got that. That's your third thing, your third criterion. So therefore, this function is an isomorphic function, mapping from G to itself. In fact, it's a automorphic function. Right? Right. So that's 4, 5. Okay. Question 5 is you have two groups, G and H. They are isomorphic. Right? So you have a mapping between them. That is an isomorphism. The mapping F is isomorphic. And in general, let H be a... Yeah. So this is question 5. So you've got G and H, two groups. So this is a general element G belonging to big G, and this is a general element H belonging to H. Right? And you're told that F is isomorphic, sorry, G is isomorphic to H. Okay? You're given that. So if little g has order n, in other words, G to the n is the unit, so that'll be E to the G. That's this group's unit. So if the order of this element little g is n, prove that the order of H now we have to assume that H is the image, the result of mapping G. So f of G is H. Okay, you're given that. Right? So we have to prove that the order of H is the same. This n. So the order of H and the order of G are the same. Okay. So in other words, translating that a bit, that means we have to prove that H to the n, the same order here, is equal to E to the H. That's the definition of the order of this element H, little h, in your group big H. Right? So that's what we have to prove. Have to show that that's true. Let's see, 9, so I don't waste time humming and hawing and thinking. Like 5, question 5. All right. Okay. Now we're told that G and H are isomorphic, right? They're isomorphic groups. So that means this mapping function f, it will obey things like this: G of G is equal to f of G, f of G. Right? This is just this thing. But we're told, we're not trying to prove they're isomorphic. We know they are isomorphic. We're told that. So therefore, this mapping F, this isomorphic mapping, has, this is true. So now, what else do we know? We're just playing around here. We know that G to the n is g to the n is equal to e to the g. We know that. In other words, the order of element little g is n, little n here. Okay. So let's put, so f of g to the n, that's the same thing as f to the g, f to the g, n times. Okay. Now, where did this come from? Well, from here. Okay. So here I've done it like I've expanded. I've got 2, and I came out with 2. And if I've got n of them, you know, g n times, I'll get f of g n times. All right. So this is f of g, f of g to the n times. Okay. Now f of g to the n here. What is g to the n? G to the n is e. Right. This n here is the order of little g. Right? The order of that element. And g to the n is e. So this is just f of e to the g. All right, now there's another theorem. You know, if you already have previous results, use them, you know, save yourself some work. Now, if you map the unit, like let's say that's the unit, e of g, it will map into the unit e of h. Right? That was a theorem. Units in a isomorphism, the units map into each other, and so do the inverses. That was a theorem. You know, go back a bit. Right. So this, if we map the unit in group G, we will get the unit of group H. So f of Eg is just E of H. All right. But this is equal to this, right? So this becomes f of g to, yeah, this is this, okay? So instead of writing this, let's put this. So f of g to the nth power. But this equals e. It's the unit of group H. All right, what is this? What is f of g? Well, it's h. Okay? So h to the n is equal to e to the h. Ta-da! All right, what does this mean? So we've shown that little h to the nth power gives you the unit. So this h here has order little n. Okay, now we've done it. All right. You could probably tidy it up a bit. Like, is it the smallest n, or you could go into that if you like. Right. Okay. So question 9 is, if you have two groups G and H, and you take their direct product. So, well, here's an example of one. So if that's G and that's H, when you swap them around, they're still isomorphic. So you're asked to prove this is question 9. So two groups, you take the direct product and you're asked to prove that this is true. Okay? So question 9, find the solutions I've done before. Alright. So we have to prove an isomorphism. So as usual, the critical step is choosing a good mapper, your function, your f, to map something to something, what to what. Well, now that's between groups. So let's talk about how do you map elements. So let that be G, GH. And that maps into H of G in general. That seems a fairly reasonable assumption. Okay. All right. All right. That seems pretty simple. That seems quite well formed. All right. Again, not much discussion. So let's try proving biject. Yeah, that's bijective. This mapping is bijective. So do you try to show that it's surjective first or injective first? Yeah, that's a question of judgment. Well, let's try to prove injective. Now, can you remember? Typically, you will take two members of your codomain, let them be equal, and if this mapping is injective, the 2 points that they map to are in fact the same point. Right?